Hello. So today I want to talk a little bit about continuity. The definition of continuity is quite short. So we say a function f is continuous at an x-coordinate a if and only if we need three things to happen. We need the limit to exist. It needs to equal some real number, not infinity or minus infinity. We need the function itself to exist, again, as a real number. Again, not infinity, not minus infinity. And then we need that those are equal, that the limit is, in fact, just equal to the limit equals the function evaluated at that point a. So that's the definition of continuous. This is maybe a little bit formal looking. On a graph, perhaps things look a little simpler. Here's some function f of x. So we're saying, okay, if this point f of a, the value at that point x equals a, if that equals the limit of the y values that it approaches on either side, then it's continuous. Meaning at that point a, there's not a hole, it's not blowing up to infinity, minus infinity, nothing like that. So that's the idea with continuity. Now, the definition itself is handy because note that this right here, what is this really telling you? It's showing you that when you have a continuous function, you can evaluate the limit by just setting x equal to a, right? So for example, polynomial functions are always continuous at every point. Right? Polynomial functions are continuous everywhere. Because of this, if you wanted to take the limit of, as x approaches, say, -1 of the function x cubed plus x squared minus 2, right? So you wanted to do that. Well, that's a polynomial function, so you can just plug in a equals -1 for all of those x's. And there we go. We get -2 as the result. So you don't have to really think about deltas and epsilons and fancy stuff like that. You could just plug in the number. It's very convenient, right? If your function is continuous. So that is convenient. But where continuity really matters is more so with the theorems that depend on continuity. This is really what I want to focus on today. So let's look at one theorem called the Extreme Value Theorem. Right, often abbreviated EVT. And this says that if f of x is continuous at every point on a closed interval, AB, then f has an absolute max and absolute min on that interval. Meaning, so we're saying it's continuous on this closed interval AB. Right, maybe out here, maybe it goes down to negative infinity, or right, maybe there's a hole over here, right? I don't really care what's happening outside that interval, but at least on this interval, I have an absolute max, and I have an absolute min on this interval. And it could occur maybe at an endpoint, depending on what the graph looks like. The way I have it drawn here, I have the max and the min both occurring on the interior of that interval. But you have a max and a min value of that function will occur on that interval, right? So there's some x coordinate where you have a max value, there's some x coordinate where you have a minimum value. So this is the extreme value theorem. This is going to be very important, extremely important in the derivatives portion of calculus, because what you're going to do is you're going to use derivatives to find places where the slope of the function is 0, and these are called critical points, and that will let you find the maximum and minimum values of the function. The extreme value, well, and you have to compare with the endpoints too. Now, the extreme value theorem itself, notice this does not tell you how to find the max or min. To find it, you need derivatives. So there's a little more theory to build there. So this does not tell you how to find them, just that they exist. So, the Easter Bunny has come and left us a max, left us a min, but it still takes some work to go find it, even though we're certain the Easter Bunny came. So what do we have next? I want to analyze this theorem in a little bit, in a couple ways, just to see, like I said, it doesn't tell you how to find maxes or mins, but I want to see if you didn't have a continuous function, why would this theorem not be true? That's what I want to look at. So here's an example. So I want to consider this function. So let's look at x squared divided by absolute value of x, right? And let's look at this on the interval -1, 1. So this function, what does this do? Well, think about if x is positive, right? If x is positive, then it just cancels. Right? Because the absolute value goes away if x is positive. So we just have f of x equals x. So I can graph that part of the function. Right, that's just y equals x over here for x positive. Then if x is negative, well, now absolute value of x returns negative x. And again, it cancels, but now it's negative x. So this is the line y equals negative x. Right. Now if x equals 0, then this quantity is 0 over 0 is undefined. Right. So we have a hole there at 0. So this function means that our function is not continuous on this interval -1 to 1 because there's a hole at 0. So on this interval -1 to 1, we do not have a continuous function. So because of this, the EVT does not apply. And f may or may not have absolute max or mins. On this interval. Right. So if you look at this interval now, and you look at the part of the function that we're dealing with, it does actually have absolute maxes, right? Here and here, we have an absolute wave y equals 1 and y equals 1. Those are the absolute maxes. So by luck, we still have an absolute max at these 2 points, -1, 1, and 1, 1. But we don't have an absolute min. The graph kind of wants to have a min at 0 as it's coming down, 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 but it never actually hits that point. It has a hole there, right? So there is actually no min. Right? So the extreme value theorem did not apply because it wasn't continuous on this interval. Sure enough, we did not have an absolute min, right? By luck, we had an absolute max. It was tied at the endpoints, right? But we do not have an absolute min. So that's just showing why continuity is so important in when you're looking at maxes and mins, right? You can't necessarily guarantee that a function has one on a closed interval unless it's continuous. Right? All right, so that's just a little bit on the idea of continuity and how it relates to one of the main themes of calculus, which is finding maxes and mins. Thanks.